I just make a remark here. It's not necessary to assume for various steps leading to the definition of Riemann integral. Let us examine the crucial steps. So here I have drawn the graph of certain function. Now what I have drawn with the white chalk is the function f, which is now not necessarily non-negative. Because some portion it is negative, takes negative values also. What do? We partition the interval. In this case 0 to we have taken to subintervals. And then on each subinterval you go for a lower approximation and an upper approximation. What you take the infimum value of f and the supremum value of f. Using them we construct a step function. And this is what you see here. Now this is the interval xi minus 1 to xi. On this we assume that the function is like this. In that case what you do? See, the maximum value or the supremum value of the function is something like this. And the infimum value mi is something like this. It is negative. Whereas in the picture I have drawn and the choice I have made, mi is positive. And it's not necessarily that mi is always positive. Now you may further subdivide this, and then on that you may get both mi and capital Mi negative. This is possible. So we can construct a step function which bounds the given function from above, as you did in the case of non-negative functions. So also you can construct a step function which is bounded below. Now you see, you cannot anymore assume that both mi and capital Mi are positive numbers. Both may be negative numbers. But certainly one thing that is certain is that your function, the graph of the function is going to be squeezed between two step functions. As you have seen here, this is a part of the step function, this is the another part of the step, the other step function which binds it from below. This is the part of the step function which bounds it from above. So it is squeezed in. And again, all those comments hold that if you refine your partition, then the lower sum moves upward and the upper sum moves downward. And the lower sums are all bounded above and the upper sums are all bounded below. Therefore, you have the supremum of the lower sums exists and the infimum of the upper sums exists. So that will give you the what you call the lower integral and the upper integral. And if the lower integral is equal to the upper integral, then you say the function f is Riemann integral. So you don't have to really go through this rather lengthy exercise. But this is certainly in the stage of learning mathematics, these kind of things, acrobatics are to be explored, and you learn a new way of handling a problem. Now, in this context, let me just suggest a beautiful book for you. That is the book How to Solve It. By Vidya. Any mathematician or any student of mathematics should necessarily read this book. And this is a book where he looks at the following question: how do you conceive a problem? How do you find a solution to the problem? And how your mind works while solving a problem. I mean, this is one of the experiences of many, that when you solve a problem, somehow you solve it without really knowing the path you have taken. But there are certain kind of thoughts that goes the subconscious, about which you are not fully aware of. So that is something looked into by Vidya, which gives an insight into your thinking on the problems, and then also tells what are the sort of clear-cut way of approaching a problem. It is really worth reading, and one should read that. And should not miss this book. It can be downloaded from the net. So I recommend this book strongly to everyone of you. Okay, so we have defined what the Riemann integrability of a bounded function on a compact interval or a closed bounded interval. Fine. So the essential assumptions that we have made are: the interval is closed and bounded. 2. The function is a bounded function. And then for those functions, we have explored what Riemann integrability means. And we found that if the upper integral agrees with the lower integral, then the function is Riemann integrable. Otherwise, it is not. So that's what we have explored, completed the exploration. Now let us look at a few examples, maybe just to quickly recall this, and maybe you do it also. This is the first example that we have looked at. F is identically equal to C on AB. So a constant function, it's a continuous function, it's a bounded function. And if C is positive, then it is a non-negative function. Otherwise, it is a negative function. In either case, one can prove that F is Riemann integrable. And integral A to B C to B minus A. This is an exercise, a good exercise to start your exploration. And you can see it is somewhat trivial, but still it's a good exercise to start with. Now we take the function here defined as 0, 1, say, or you can take any interval. For that matter, you can take it as Then depending on AB, this function may be non-negative or may take even negative values, may take fully negative values depending on A and B. And you can see the graph of the function is, as you know, if A and B are here, then the graph of the function is this. Is the graph of the function. You are actually computing this here. Okay. Then you can once again try to go through that exercise, whether this is Riemann integrable or not, and show that both the upper integral and the lower integral are equal in this case, and this is given by integral A to B equal to what you have. You have got this as b square by 2 minus a square. What was that? This is a good exercise, not as trivial as this one. So then we do this first and then go to the next. And then of course the third example is, once again I recall the division function, so that these three exercises, now you see the division function is bounded. It's a bounded function, it's a non-negative function, so all the exercises can be looked at, and you will see that the what you call the lower integral is different from the upper integral. In fact, this is what you get. Integral a to b equal to 0 is less than b minus a and equal to a to b, the upper integral. Clearly, the lower integral is not equal to upper integral, and therefore this function is not. So, what next? There are two things that we have to do immediately. One, you ask the question, do you have a large class of functions Riemann integrable? Or is it just a handful of functions? So this is one question. If it works for a large class of functions, then our exercise is really worthwhile. Okay, so this is something to be explored. But I believe before that, we see this operational strategy to decide whether a function is Riemann integrable or not is a bit cumbersome and probably not easy to work with. So we explore equivalent forms of this condition. This is what is called proving characterization theorems. So we have defined something, and if you can prove that this is equivalent to something else, and if that something else is more easily verifiable, then you are simplifying your task. So this is the strategy. So you see that our definition is fine, it's well defined, nice, and everything is wonderful about it, but given a function, sometimes it may not be easy to check this. So let us ask, is it possible to characterize the Riemann integrability? That's what we are. So let me now take out this. And then at least give you a characterization theorem. And I would suggest that you go to explore to prove this. The equivalence of the theorem I write with the integrability condition that we have already set. So that will give you a good experience of working on analysis. So our question now is there a better, a more workable way on Riemann integration? Equivalent to what we defined. This is a question. Let us explore this. You see, if you explore this, this is something that we had. We had integral a to b. You take the lower integral of fx dx. This is less than or equal to integral a to b, the upper integral. And you also know that this is true, that for any partition G of AB, we have the lower sums as we have defined earlier is less than or equal to integral a to b, which is less than or equal to u. So you see that both the lower integral and upper integral are squeezed between the two numbers, namely LPF and UPF for any given partition. Therefore, if you can somehow work on LPF and UPF, then you don't have to go about evaluating the upper integral and lower integral. This is much easier to work on. Why it is easier to work on? Because they are here what is involved is working on step functions and computing the area, which does not involve any integration or any such thing. It is just area of rectangles summing up. So that is much easier to work on. Therefore, if you can reduce to some conditions on LPF and UPF, then you get a better criteria. So what we want is that these two to be squeezing out this. Okay? Or in other words, what you want to say is that, see, this is the scenario that you have. You have LPF and you have possibly UPF. Or UPF for all P belonging to, it is scattered over here, it is scattered over here. And you are talking about the infimum and supremum. If it is not Riemann integrable, what happens is that there is going to be a gap here. And this gap you cannot fill. It is not Riemann integrable. But if it is Riemann integrable, what you get is that this is going to be the same. So what you get? So you can see from your experience on working on sequences or numbers bounded, then you see that if this is possible, provided, because what you are saying is it is the supremum of LPF and the infimum of UPF which are equal if it is Riemann integrable. What does it mean? Since you are talking about the supremum and the infimum here, since it is supremum that we are talking about, there is an LPF which lies arbitrarily close to the lower integral. There is a UPF which lies arbitrarily close to the upper integral. Or in other words, you can find a partition for which the difference between UPF and LPF will be arbitrarily small. This is the whole idea. Okay? So let us write down the theorem. Because it simplifies your task, because you need to calculate only LPF and UPF, which are just working out, working on what are called step functions. Okay, so let us write. The following statements are equivalent. So we give three statements which are equivalent. One of the statements is that F is Riemann integral. So the first statement is in the sense that the upper integral is equal to the lower integral. That's it. Now an equivalent statement would be the following. This is merely expressing Riemann integrability in terms of LPF and UPF. So for every epsilon positive, there exists a partition P, set of all partitions of AB such that is less than. As I pointed out here, you can find a partition for which there is an LPF here, there is a UPF here, and suppose your epsilon is this big, then you can find the LPF and the UPF such that their difference is less than epsilon. If you choose a still smaller epsilon, still you can find a partition P such that this is true. This is possible. This is a outcome of the definition of the upper integral and lower integral, and the assumption that the upper integral is equal to the lower integral. Okay. Now a third form, equivalent form is this. There exists a unique real number alpha such that for every partition P of AB LPF is less than or equal to alpha, less than or equal to U. And this is very important. There exists a unique real number alpha. The uniqueness is important here. Such that this is true. Now, why uniqueness? What happens if it is not unique? If it is not unique, then you are going to have LPF less than or equal to alpha less than or equal to less than some beta less than or equal to, where this is going to be this may not be the supremum or may not be the infimum of this, but there are two numbers like this. But certainly you are sure that you cannot find a partition which will bring it more closer than this. So for any epsilon that is smaller than beta minus alpha, you cannot bring them closer, or you cannot bring them closer than beta minus alpha by a choice of P. So in that case it is not Riemann integrable. But what we have to show is that if there exists such a unique choice, then you always have this. I mean, that is quite easy to do. Right? So just make a couple of remarks on the proof of this, but we will not go into the proof of this. You can go to any book on Riemann integration to find a proof of this result. Okay? Especially to the book I suggested, written by Indarvana, where a detailed proof of this is discussed. Okay. What do you do? Let us go back here. Now you see, you can find a partition P such that LPF, you take the integral. What is that integral? The lower integral. The difference between LPF and the lower integral is less than epsilon by 2. That is possible because this is the supremum of these numbers. So also you can find a partition P such that the difference between the upper integral and UPF is less than epsilon by 2. Okay. Therefore, for that partition, you see that the difference between, say, one of them is, say, for the lower integral, the partition you call P1, for the other one you denote it by P2, and then you see that P1 union P2 is a refinement of this partition, and call that P, and for that partition, this condition will be satisfied. So once it is Riemann integrable, that is, if you assume condition 1 is true, then you prove that condition 2 is true. Okay? And then you assume 2, that the second one is true, and then prove that the first condition is satisfied. That is, the difference between the Riemann, the upper integral and the lower integral, or the upper integral is equal to lower integral. Why is it so? Because you see that UPF is always less than or equal, LPF is always less than or equal to the lower integral. UPF is always greater than or equal to the upper integral. So for an arbitrary epsilon, you can bring their difference less than epsilon, then you see that certainly you are assuring that the difference between the upper integral and the lower integral is less than epsilon. Okay, so for an arbitrary epsilon, you are proving that the difference between the upper integral and the lower integral is less than epsilon. What does it mean? It means they are equal. Okay, so I just gave a hint to the proof. Now it's for you to work on the proof, if possible, all by yourself, and possibly you can take the help of a book on measure and integration. At least the initial stages you can look at and study how the proofs are written, what kind of theorems or analysis are made use of, and so on. So thank you very much. That is the end of the episode 4, and we carry forward our mission further and take up new ideas on Riemann integration. Thank you very much.